what we're going to look at here is changing the rate of our reaction. Right? And at the same time as changing the rate, it also brings in this secondary effect of favoring one product over another. Okay, so when we talked about changing the rate before with our electrophiles, what did we do? So if we took a look at this first case, how does that reaction sped up? Added the aluminum trichloride. What did the aluminum trichloride do? Acted as a Lewis acid that did what? Helped polarize our bond, and it was reformed in the course of the reaction. We get the Lewis acid back, which means our acid acted as catalyst. Right? In the case of our nucleophilic rings, can we potentially add something in to catalyze it? Okay, so can we somehow add another species that indirectly gives up its electrons to the ring without changing the structure? Well, carbon all has its octets. There really isn't anything left. Okay, so what we're going to have to do to speed the reaction when we're looking at the nucleophile is physically changing the ring. We're going to have to add something to that ring different from hydrogen. Okay, so in the cases drawn up here, what is atom X on top? What can you tell me is special about that atom versus hydrogen?
More electronegative.
X could be anything. Does that necessarily mean that it's more electronegative? I think I know where you're trying to go with that. Remember, electronegativity is dependent on what atom it is. Odds are it probably is, because hydrogen is so low, but I haven't specified what that atom is. Atom X has more electrons than hydrogen. That's why there's a lone pair. Right, that lone pair is a big significant standout. So if atom X has more electrons, that's going to change how our overall reaction works. We know where atom X directs, but would we expect that to speed our reaction? Right, well, to make our reaction go faster, what charge do we expect to build on the nucleophile? Nucleophiles are nucleus-loving, so it needs to be negatively charged to react with the nucleophile, or nucleus. Okay, so our ring needs to somehow build a negative charge. Does anybody see a negative charge on that ring? Is there a little minus sign with a circle around it? No. So if we're going to try and find charge, what should we do? Start moving electrons. What electrons do I start to move? I can move the pi bond, but I'm going to make a pretty solid argument, in my opinion, that the pi bond isn't going to be particularly relevant to move. Why not move the pi bond?
Because it stabilizes the ring.
No. We're trying to see how atom X affects the ring. If we just go through and move the pi bonds, we aren't showing an effect of atom X. So we're concerned about what atom X can do. So atom X happens to have a lone pair of electrons. What can we do with electrons? We can move them. So our focus starts with atom X to see what happens. Okay? This is how we would go through and draw all resonance structures. So we go through, we did one move, and we now draw to see what the result of that motion is. And as a big kind of emphasis on here, we now draw. Okay? I'm still noticing this is a big problem for my older students and with the newer students. Okay? If you do not draw, you will get the answer wrong. Okay? Draw it out. And yes, Sapling will make you draw it out. I will specifically put some questions in there where you have to draw it out. Right? It will help you. So if we go through and draw everything in, because I'm telling you to do it, I'll go through and do it myself as well. There are all our hydrogens. Right? There's my X. I didn't touch any of the pi bonds yet. Okay? And my arrow shows that the electrons moved in to form a pi bond between atom X and carbon. That is what my arrow shows. Okay, those of you drawing this hopefully aren't drawing in pen. What is wrong with this structure? Too many bonds on carbon, which inherently means that this answer is wrong. So before we just give up, we go back to where we started or look at this structure and say, is there other electrons that we could have moved to have stabilized this? Okay? So that's when we look at our weakest point, that carbon, and say, do we have available electrons to move? Which in this case has to be pi bonds. We have 2 pi bonds. Which pi bond should be moved? The one in the ring. Why? Because if I move the one on X, what I would need to do is go back to my drawing. I move the electrons from X into the ring, and then I do what?
Then you're back there.
I move them right back out. That was completely useless. I did nothing. So what I want to do is move the other pi electrons. Now the question is, where do I move them?
Well, technically, you're going to the carbon, but can't you just skip over and go back?
There really is no technically in this case. We can move these electrons however we want as long as we're moving within our rules. The ways that we can move electrons are from atom to bond to atom, and bond to bond. Bond to bond is officially a shortcut. Okay, really all we're doing when we're moving electrons is we're going atom to bond or bond to atom. And it has to be directly next to it. We can't jump things. Okay? When drawing resonance, minimize the bond to bond electron pushing as much as possible, because it is cutting out one of those possible structures. So in this case, I'm going to move the electrons from the bond to the atom and not bond to bond. Feel free to draw it out to bond on your own time, and you will see what you end up doing is ending in a loop where you end up pretty much right back where you started. All right, so now that I've done that, I go back to my structure, move the electrons down to form the pi bond. I move the electrons from the pi bond to now a lone pair on my carbon. So, all right, we'll come back to that in a second. Everybody okay with the bonds? See how those all moved? Okay. Here's the next biggest issue I'm noticing a lot of students making as mistakes. This is not a correct Lewis structure. If this is provided at any point for an answer, you are wrong. Okay. Whenever you draw out a structure, there's one last step that you must do every single time. What is that last step? Calculate formal charges. Okay. For those of you that don't remember how to calculate formal charges, don't worry, you're not alone. Formal charge equals, this is my method, the number of valence electrons minus the number of non-bonding electrons. I don't say lone pairs because pairs assumes a pair of electrons and that messes up your count. Minus the number of bonds. Where do you have to calculate formal charges? Everybody's going to love this answer. Every single atom, you must calculate the formal charge. When can you stop calculating it for every single formal charge? When you stop leaving formal charges off your structures. Okay? So, what does that mean? That means to calculate, I'm going to start with hydrogen. What is the formal charge of my boxed hydrogen? Well, hydrogen has how many valence electrons? 1 minus the number of bonds. 1 minus the number of non-bonds. 0, which gives me 0. Next, hydrogen. This should be very tedious. Okay? The whole point of going through and making you calculate the formal charges is to get it beaten into your head that when something is outside of the standard realm, you just know what the charge is and you don't have to calculate it. So every single time you draw a structure, from now until next week, draw the formal charge and calculate it for every single atom. Yay. Okay. So as we continue to go around, eventually what we'll end up finding is we'll get to this carbon. What's special about that carbon? It has a lone pair, which means we're going to get a different odd count. How many electrons does carbon bring in? 4 minus number of bonds
3,
minus the number of non-bonds,
2,
which gives us
minus 1,
-1, which means
negative charge.
-1. I notice everybody's looking like, this is boring, I know how to do this. No, you don't. I'm sorry, you don't. Okay? I've consistently seen everybody do this wrong. Okay? What's our overall charge now? -1. Is that our answer? We found a formal charge. Yay, that makes sense. What can we do to check to verify that we actually did this correct?
Should be neutral.
Just a sec. What's the question?
I have a question on the number of bonds, actually.
Yes.
2, why is it 2?
It's, I definitely didn't order that right. Let me change that order around to match the formula. So it's 4 minus the number of non-bonding electrons, which is 2, minus the number of bonds, which is 3. I did do it out of order. I was afraid you were going to ask. It's my fault. If you're ever concerned that maybe you didn't calculate your formal charges appropriately, okay, so this requires that you did it at least check most of the structure, we can also go through and check it another way. The overall charge, as you move from reactant to product, does what? It does not change. So if you have balanced your equation, which is questionable, it's organic chemistry, but if you've balanced your equation, the formal charge does not change. What is the charge on the reactant right now? Charge on the reactant, very first, the leftmost structure. Neutral. There is no charge shown. What's the charge on the structure that we've drawn out? -1. What does that mean? We missed a charge. Something is wrong with our answer. Before we move on to the next thing, we need to fix that first.
Would it be
Okay.
the atom we took the electrons from?
Yes.
So the X would be positive?
The X has to be positively charged. Can we use the formula in the case of X? No, because we don't know what X is. Okay? So is there another way to calculate formal charge? What charge was X to begin with?
Neutral.
Neutral. There's no charge. What did it do with that first arrow?
Gave us electrons.
It lost electrons. If we lose a negative charge, what happens? You become positive. There's your positive charge. Okay? What does this do as far as the speed of our reaction? What charge is the ring now? I didn't say the structure, I said the ring.
Neutral.
The ring is negatively charged. The atom X is outside the ring. Our ring is now formally negative, which makes it more or less nucleophilic. More nucleophilic, which then means I would expect this structure to react faster. Atom X gets a fancy name in this case. That name is activator. Because apparently we watch too much Transformers. Okay, we now have an activated ring. What happens in the case of the bottom X, where X is positive? Okay, we're still concerned about how X affects our ring, but we can't draw electrons down into our ring anymore because atom X doesn't have the electrons to donate into the ring. So we still want to focus on atom X, but what we're going to do is get it an electron source. That electron source is the pi bond is drawn out of the ring. What's the result? I now form a double bond to our X. What happened with the rest of the structure? Atom X started positive. The arrow did what? Added electrons. So if I'm positive and I add a negative charge from electrons, what happens? Goes neutral. Okay, so atom X is no longer charged. Cool. So there we go. I got my answer. I moved the electrons. There we go. What's wrong? Charges don't add up. I started now
You started,
positive,
Yeah,
and now I've ended neutral. Again, I've somehow destroyed charge in the process of this. What did I miss? The positive charge on the carbon. What charge is the ring now? Is that more or less nucleophilic?
Less.
Less nucleophilic, meaning the reaction's going to go slower. Okay? So let's look at a summary on this. Atom X, in the top case, has more electrons than the hydrogen atom. This makes it an activator. We'll get at the para-ortho in just a second. In the bottom case, the X has less electrons than a hydrogen atom. That means our ring is deactivated. All right? How can we have less electrons than a hydrogen atom? This is always a tricky question. How many electrons does a hydrogen atom have? Oh, you knew the answer. That's cheating. Hydrogen atom has 1 electron. So how do we get less electrons than 1? 0 could work, but that's not going to help us out because we'll never get 0. Become charged, but you become positively charged. You've lost those electrons. So any atom that can put a positive charge on it becomes a deactivator. Yes, we can run into weird, tricky situations where that isn't perfectly the case, hence the lab. Okay, but for the most part, if you can put a positive charge on atom X, okay, it is a deactivator. The next question comes in with, or actually before we do that, are there questions on that? So what we've done is used resonance to start to predict something about the reactivity of an individual ring structure, okay, whether it reacts faster or slower. Okay, that can help us out when we move into lab, but in lecture we don't really care about how fast it goes, we just want to know where it goes, which is what I had you guys do with the quiz. Okay, depending on your structures, you ended up putting the electrophile in a different position. That different position was dictated based on your intermediates, and what we were hoping to find is there some kind of pattern that we could use to overlay on this so that we don't have to draw out those resonance structures. Turns out if you do go through and draw all of our resonance structures for our starting materials, all right, let's take a look at atom X up top being red. Where's their negative charge in the next structure over? That is located at what position?
This is ortho.
We have our ortho position. In the next resonance structure, where's the negative charge?
This is para.
It's in the para position. Next structure,
Ortho.
ortho. Where would I expect my reaction to occur?
Ortho and para.
In the ortho and para positions, because my ring needs to act as
Ortho and para.
a nucleophile, which means it needs to react where there's electron density. Those are the 3 positions on the ring that have the most electron density, thereby suggesting that if I have a structure that fits under this pattern, that is an ortho-para director, a para-ortho director. Why para over ortho? The steric hindrance argument. Para has less sterics, we would expect the para substitution to happen first. What happens in the lower case? Okay, where X has less electrons than a hydrogen atom. What charge builds on the ring? Positive charge at the ortho position. Next structure. Para position. What charge? Next structure. Still ortho. Anybody see an issue here where this could get tricky? We're putting charges only at the ortho and para positions. Okay, in both cases. But in one case it's negative, other case it's positive. So don't memorize where you're putting the charge. Memorize how the charge got there. Okay? When it's our activator, that's a little bit nicer because we put the negative there. Those are activated. Those positions are awesome. But what's happening with atom X at the bottom? We're still putting charge at the ortho and para positions. But those charges happen to be positive. Our ring needs to act as nucleophile. For it to act as a nucleophile, what charge needs to be there? A negative. So would I expect a reaction to occur at the ortho or para positions? Absolutely not, because there is no electron density. Okay? So we would expect this reaction to go extremely slow because the ring is positive. It doesn't have any electrons. But if I gave it enough time, where would I expect the reaction to occur? The meta position. Why?
It's not positive.
It's the only place that has some electrons. All the other positions have no electrons. Okay? So our deactivators are meta directors, meaning that if you have it start with a ring that has a deactivator on it, it's going to direct the substitution to happen at the meta position. It'll just take a lot of time. With all the problems that you're going to see both in the sapling, in your textbook, or on your exams, we don't really care about time. Okay? All we care about is where those positions go. Questions about that? Three.
View on the meta position be occupied.
What's that?
View on the meta position be occupied, like be attached to some.
If we started with that bottom structure, we would expect our substituent to go to the meta position, to do the substitution of a hydrogen at the meta position and the meta position only.
Yeah, and all meta positions will react, right?
All the meta positions, they are not activated, but they are the only positions that can react. And there are two of them in this case.
Right.
What's the difference between those two?
One closer to the X. No?
What's the difference between the two meta positions?
Oh, they are the same. Right?
They are exactly the same. There is no difference between them.
So they react the same way.
They will react the exact same way. Sarah, did you have a question? Okay. So we need to follow the patterns of our overall structures. So we talked about electrophiles last week. Now what we're doing is making it more difficult because the nucleophile we're starting with is not just benzene. And we're going to tweak it and put on some other piece. That other piece, you need to go through and decide what that piece is. The atom X, the very first atom attached to the ring. Does it better match having more electrons than hydrogen or less electrons than hydrogen? That's going to determine where your substitution will go. Okay? So we take it back to the quiz. What was our atom X for number 4? Carbon, right? Which does it fit? More electrons or less electrons than hydrogen? We can put a formal positive charge on that carbon, meaning that carbon has less electrons than hydrogen, which means where do we expect the substitution? Meta position. Holy crap, we got the exact same answer that you guys spent so much time figuring out. Good job. How about with question number 1? What was atom X? Again, it was a carbon, but this time, can I draw a formal positive charge on that carbon? No. So now I'm just stuck with a neutral carbon. Well, neutral carbon and neutral hydrogen. Which one has more electrons? Carbon, which means atom X in this case is activator, and I expect the para or ortho substitutions. There's my para product. Okay? Didn't need to draw out all those resonance structures. Made you do it anyway because our lesson is when in doubt, draw it out. Yes. Was that, oh, dang it, hopefully not towards that statement. Yes?
Is there any way we should memorize it or not? Like which group is activating, which group is...
The only way you should memorize it is what is atom X, period. The textbook will list out a whole bunch of different examples. You are more than welcome to memorize what the textbook tells you to do. But if you look at those structures and identify what atom X is, does it have more electrons or less electrons? It fits. There is no point in memorizing specific substituents because all I will do is give you a different substituent that was not on that list, and you are now stuck. Understand why, where they're coming from. All right? You got enough other things to memorize than just memorizing random facts. Okay? Next issue we're going to run into is, remember when we talked about the Friedyl Crafts alkylation and acylation? I said, or had a brief mention there that our alkylation required an active nucleophile. Okay, so what does active mean? Our active nucleophile means atom X
Has a lot of electrons.
has more electrons than hydrogen. Think back to the quiz. In fact, yep. If we take a look at the quiz, question number 4. Yep. It was this guy. The answer you provided, we got up on the board, we did the meta substitution. Are you correct? Is that answer correct? Would we expect the meta substitution product? This is a fun one on a lot of tests. You will see this as an answer. Guaranteed that's one of your multiple choice answers. This is also one of your multiple choice answers. What's your answer, left or right? The rightmost structure. Why? Nope.
Why CH3?
Oh, I see what you're saying, yeah. Thank you, I can fix that. Still the wrong answer.
So it's not that the reaction didn't occur, it's that didn't it just go back to the original?
So this is a fun, how are we phrasing the question? Okay, so we can go through and say reaction didn't occur, or what we can do is say what product was isolated, where product is in massive air quotes that is implied. Okay? What we isolated was the starting material. We didn't get a new product because no reaction occurred. The question becomes is why did no reaction occur? What type of reaction were we attempting to do?
Substitution.
It is a substitution reaction. It might be up at the top of the slides. A Friedyl Crafts alkylation. Special conditions for the Friedyl Crafts alkylation requires an active nucleophile. Atom X must have more electrons than hydrogen. Where's our nucleophile? The ring. What's atom X?
CH3CN, isn't it?
Our carbon on the ring. Does that carbon have more electrons than hydrogen? No. Through resonance, we generate a formal positive charge on that carbon, which means it is a deactivated ring. The deactivated ring will not react under Friedyl Crafts alkylation reactions. We get no product. We get our starting material. Okay, so the Friedyl Crafts alkylation already has some problems. Okay, it doesn't want to react right away, okay, unless we have an active substrate. So if you looked back at that quiz, there was an extra credit thing that said, which of these reactions produces no product? Sorry, group number 4. Okay, officially that answer was no product there. Okay, for the sake of the quiz, I just wanted you to go through and draw out what those possibilities were. Okay? Before we get into that question, what's your question?
So it's because of the positive charge on the carbon that's outside of the ring?
Yep. Atom X, that carbon, has a formal or a partial positive charge, which means it has less electrons than hydrogen. It is a deactivated ring. It does not work in Friedyl Crafts alkylations. The acylation, which is the reagent below, does work. Why would the acylation work but not the alkylation? until it comes all the way down to these two species. And actually, there we go. Our acylation will always work. Alkylation won't. Why? What's the difference between those two circled species? They're both positively charged.
You have electrons in the second structure that allow for stabilization of the.
For our EAS reaction to work with these electrophiles, I have to form those electrophiles, so they must have some stability. If there is no stability, I can't form them. If I can't form the electrophile, I can't do the EAS reaction because there's no electrophile. In the case of the alkylation, it's just a positively charged carbon. There is no stabilization of that. So a tertiary substrate would be better, okay, because I can form a tertiary carbocation that's relatively stabilized. In the case of the acylation, what was special? It's not just the pi bond, it's the fact that that oxygen has lone pair electrons, which can be donated down into the carbocation to resonance stabilize the intermediate. If we have a stable intermediate, we can now potentially move that on into a reaction. Until we have that stable intermediate, we can't move forward. So the acylation is nice because we have that stabilization, okay, to allow us to move forward. So given the choice, which reaction do we run? Probably the acylation. But what if you only wanted carbons? You just wanted a long carbon chain. Acylation is still going to be the best option. Because if we think back to the summary slide, after we acylate, what could we do? We can reduce the carbonyl off and take it right back to the alkyl chain. All right, so we have to run 2 reactions instead of 1, but those 2 reactions get us to our product, whereas the 1 reaction doesn't work. Okay? So the acylation ends up being the preferred reaction when you go through and deal with putting carbons onto rings. Okay? If that wasn't bad enough of a death tone for our alkylation, we have another issue. Okay? So let's do our alkylation problem again. Except this time, we're going to use an activated substrate. How do we know this substrate is activated? What is atom X? What's our nucleophilic atom X? The oxygen. Does it have more electrons or less electrons than hydrogen? More electrons. We can do resonance, putting the negative charge on the ring. We can absolutely activate it. We would absolutely expect to get a substitution in this case, and we would expect that substitution to occur at what position? The para or ortho positions. We prefer the para because sterics. So good, we've got that. Okay, but remember, we're running this reaction in a big volume. We've got lots of concentrations of these things. Compare our starting material with our product. Which of those is more activated? O is right. In our first structure, we had 1 atom X, our oxygen. In our second structure, what are our atom X's? Got the oxygen and carbon. Those are both activators, meaning our product is now more active than our starting material. So we run the reaction once, we produce a product. Now our product is actually more reactive than our starting material, so what happens? The product reacts, not our starting material. And we put on yet another methyl group onto our structure. What does that second methyl group then act as? Another atom X, and that other atom X happens to have more electrons than hydrogen. Our product is yet again even more activated. So what ends up happening is what's known as polysubstitution. Okay? And we end up, under the Friedyl Crafts alkylation, not putting on a single electrophile. We put on a ton of them. Okay? So as a reagent, our Friedyl Crafts alkylations are very dicey to deal with. because we have to start with an activated nucleophile as a requirement, and we also have this issue of a polysubstitution happening. How do we know when it does the polysubstitution? That's a lot more challenging of a question to answer, and hopefully we don't run across it. Okay? We would hope that at some point in the question it's going to specify or provide a little extra information to hint at the idea that we're going to do it multiple times. Okay? Why does the acylation not give us this problem? Oh, remember, did I provide the structure? I did not provide the structure, so let's try that again. We'll run the exact same reaction, exact same starting material, except now, as my reagent, I'm going to go through and use this guy. What's my product? Don't all shout it out at once. Okay, we would expect our para or ortho positions, and at that position we would expect the acyl group. Everybody relatively okay with that?
Yeah.
Why do I not expect polysubstitution here? We do run into a little bit of hindrance, but that's not going to be the issue. Sorta. I don't quite accept that. Our atom X, we still have our oxygen. Okay, I was about to erase everything. What's our other atom X?
Carbon, right? Carbon.
Is that carbon activating or deactivating?
Deactivating.
Deactivating. What happened to my product now? It is now less active than my starting material. So given the choice, which one's going to react first? The starting material. I should end up with cleanly one product. I don't have to worry about this polysubstitution because in the process of running that reaction, I have deactivated my product from being able to react further. Right? So the acyl substitution is probably one of your best bets when trying to go through and put on the carbons. Okay? Questions? Just as a general survey. Been hearing people complain that lecture's been going way too fast. You feel relatively comfortable with what we've talked about today, more so than others? A few yeses. Okay, I'll kind of accept that. Good enough. Okay, no lecture on EAS is satisfied until we drop in our lovely halogens. All right? How would we expect our halogens to act? Are they activators or are they deactivators? So we take a look at an example. We've got our categories in both cases. Our halogens, do they have more electrons than hydrogen? Yeah, they got 3 lone pairs. They absolutely have more electrons, which would suggest that they are activators. Okay, so that means the halogen has to donate its electrons to the ring. Wait a second. Would I expect a halogen to donate electrons?
No,
Why not?
they don't share.
Why don't they not share?
Because they just need one to fill out.
They are highly electronegative. So our halogens are now straddling right in the middle with our definition. It's a bit obnoxious. Okay, so where do they actually fall? Okay, that's kind of the fun part with this. They are what I would classify as the one exception with all of our EAS. Because they have the lone pairs, there is this pseudo-resonance effect that builds more electron density at the para and ortho positions. So because of them having more electrons than hydrogen, we expect them to be para-ortho directing. However, they don't want to give up their electrons, so they are deactivators. So that's where you have to be careful. Activating and deactivating is separate from our directing effect. It just so happens that previously our activators went to the para and ortho positions, and our deactivators went to the meta position. They are separate concepts. The halogens are the ones that define that line. So halogens will deactivate the ring, okay, but they direct to the ortho and para positions for substitution. Okay? So when you asked about which substituents should you have memorized and what they mean, memorize your general rules of what X is, more electrons or less electrons, and then throw in the hydrogen or the halogens on top of it. Okay? Because the halogens are the ones that break that rule. Okay? So the rest of the slides that I would hope to get through today are pretty much just examples. Okay, so if we've got multiple substituents. Okay, for that first question, what would we expect to happen? What's our reagent going to do? It's our electrophile. I'm going to go a little bit more than bromine, put it positive bromine. Okay? Which then means for a product, I'm going to then substitute somewhere on that ring a hydrogen for a bromine. Are all of those hydrogens the same? I think we can make an argument that these hydrogens are the same and that these hydrogens are the same. Where does the substitution occur? Substitution was dependent on what atom X was. What's atom X? Carbon and our nitrogen. For those of you that don't know already, let me draw out the Lewis structure for our nitro. Okay, where does the methyl group or our carbon activate? Atom X, that's the carbon, activates where? Para and ortho, because it has more electrons than our hydrogen. So para and ortho are valid positions. Can I do a substitution at the para? Why not? There's no hydrogen. I need a hydrogen. So I have to go ortho. What about from the nitro? The nitro atom X is deactivating, which would suggest meta. Where's the meta position? Purple or blue? It's blue. Why is it blue, not purple? It's meta to whatever you're looking at. Meta and ortho and para are all relative locations, relative to whatever atom you've decided is your center. When we move to the nitrogen of our nitro, we've now decided that's our center. Our meta position to the nitrogen are our blue hydrogens. The result being, where would we expect to put on our bromine? Okay, we would assume to run it once. Okay, we could try and do it twice. It's probably not going to happen twice because we have that nitro group which deactivates the ring, so it's going to slow it down. We then also put on a bromine, which was also deactivating. 55 or 50? Okay. What about the next one down? What's atom X? Oxygen and carbon. Where does the oxygen direct? Para and ortho. Can we substitute at the para position? Nope, because there's no hydrogen attached to the para position. So it's got to go ortho. So we would expect our substitution to go at one of the ortho positions. Because they're both identical, I'm just going to mark one of them. Let's take a look at our methyl. Where would I expect that to substitute? Para and ortho. Para and ortho to the carbon. Well, the para to the carbon is occupied, so I can't do that substitution. So where does it direct? Interesting. we now run into a conflict. All our hydrogens are activated. Where would I expect to put on that new electrophile? Goes to the red position. Why? It has to do with the relative activating abilities of each of our reagents, or each of our atom X's. The oxygen is more activating than the carbon because the oxygen has lone pairs that can physically donate in through resonance. Okay? The stronger the activator, the more dominating its effect on the overall ring, which then means it's going to dictate the chemistry. We expect the nitro to go para or ortho to the oxygen, not to the carbon. Okay? So we can start to run into a couple rules. Your textbook breaks it out into 3 or 4 rules, which really just boil down to 2 things. Okay, number 1, your activators will always trump deactivators. In fact, we can actually boil it down to 1 rule. Okay? The stronger the activator, that one dominates, period. Okay, so activators will always trump deactivators as far as locations. The stronger activator trumps weaker activators. It's the same thing as activator trumps deactivators. So when you look at a ring and you got multiple substituents on it, identify the one that is most activating. That's where your chemistry is going to be based off of, that position and that position alone. Okay? So, we run these reactions for the sake of time. We're going to end up with 2 possible products. What product do we expect as our highest yield? Actually, let's go back one. For that first reaction. Left or right? In this case, we've got as our atom X's carbon in both cases. Very subtle difference between those. We're now going to run into another issue here. Our activators are, for all intents and purposes, the same. How do we decide which position gets substituted? Moves to sterics. We start with resonance, we move to sterics. Which one of those has the least sterics?
The second. No, the first.
The one on the left has the least sterics. The nitro group is going closest to the methyl as opposed to the isopropyl. If we move to the next one down, they again show only 2 products. There was a third possibility, and you kind of wonder why I didn't show that. Why did they not put it in this position? That one's got the absolute most sterics of all of those positions. So we really should have shown that. I didn't. It's my fault. Okay, but that one absolutely doesn't make sense. Between the 2 products now shown, which one is better? The one on the left. Again, because sterics. Okay? So when you're going through and dealing with your EAS reactions, start with resonance effects, then move your way into sterics. Ideally, you don't have to deal with sterics because that's usually a gray area on deciding everything. Okay? We'll finish on this slide. How can we get from the left to the right? What reagent? What changed, first off? Let's stick with that. We added bromine. How do we get Br+? Good. We run this reagent. What product do we get? As a hint, not the one you were actually expecting to get. We get this as a product. We wanted the ortho. How can we get the ortho? Block the para position. There is only one reagent that you have, okay, at least at this point, that allows you to block a position and then also remove it at the same time. What we would go through and do, H2SO4, which is the sulfonation reaction, which puts on your SO3H. Then you can do the bromine reaction. Your para position is now blocked by the sulfate. And then we have to do the reverse of the sulfonation reaction, which is H2SO4 again, but in the presence of large amounts of water. Okay? That will pop the sulfate group off. We now have a very high yield of our favorite bromine product. Okay? Just as a random mention, because this reaction is in disfavor, okay, why is this a bad reaction to run? All sorts of issues pop up with it. Number one, the sulfuric acid you're using is highly concentrated to the point that it's fuming, kind of dangerous. Okay. Number two, we did in 3 steps what could have been done in 1, theoretically, if we had planned our experiment better. Okay. So this reaction is not popular because it is not green chemistry. You used a whole bunch of dangerous toxic chemicals that you didn't have to use, and if you had designed your experiment in a better way, you wouldn't have had to use those chemicals, and hence you are now not being green. Okay? Just an important thing to kind of consider when going through some of the background stuff that you're dealing with. Okay? We'll pick up with predicting how to make that product, starting with benzene on Wednesday, and we'll see where we get from there. Okay?